Yeah, everybody. Let's introduce Fabio Bacchini from KU Leuven, who's been doing a lot of like simulation and modeling of stellar plasmas and ultimately, I guess, the overall stellar magnetohydrodynamics. Yeah, welcome.
Thank you very much. Then I would go ahead. Thank you, Greg, for inviting me. Thanks for the introduction. Also, I am indeed currently an assistant professor at the Center for Mathematical Plasma Astrophysics of KU Leuven in Belgium, and I'll talk a little bit about my work on astrophysical plasmas. Yes, you can go ahead. For the people who don't know where KU Leuven is, as I was saying, I am based in Belgium, in Europe. I myself am right now a professor, which means that I did the whole trajectory that we go through to get to where we are. I was a PhD here at KU Leuven, actually. In 2018, I got my PhD in astrophysics. Then I went through some postdoctoral positions in Germany, back to Belgium, then USA in Colorado. And in 2022, I came back as an assistant professor here, where I am slowly but steadily building my own research group, which at the moment consists of 7 PhD students and 7 postdocs. Depending on how you look at it, I have some co-supervision students who augment this number. I teach at KU Leuven. I teach fluid dynamics and I teach plasma dynamics, and then I also do my own research, focusing on heliospheric plasma physics, high energy plasma physics, and then also a little bit of high performance computing and numerical methods. And so I already mentioned the word plasma a few times, and I understood the description that I was given that this audience is a bit diverse, and therefore it may require some introduction to the subject. And the introduction to the subject that I usually give is that at this point in time, a lot of people have heard about plasma, I think, from elementary school to high school. You may have been told something like the state of plasma is the 4th state of matter. That's usually how it's marketed, I would say. Therefore, if it's described a little bit more in detail, usually it's presented as something like a state of matter where a gas has its own individual charged particles now split from each other. So electrons and protons in atomic nuclei are free to move around without being linked or bound to each other. So that's usually how it's presented, I would say. Now, what maybe not exactly clear from what we are told in school, or in general, if you don't really study the subject, is that plasma is, in fact, the most common state of matter in the universe. If we look at the universe on a global scale, then the plasma is the state in which most of the matter is found. 99% of all matter in the universe is in the state of plasma. Plasmas are found on Earth as well as in space. And on Earth, we may see plasmas without realizing it. For example, the auroras that are seen in many parts of the world. There were auroras even at the latitudes of Belgium a couple of weeks ago, actually. So auroras are in fact a manifestation of plasma activity in the atmosphere of the Earth. And the auroras are a light that results from plasma particles entering the Earth's magnetosphere, essentially. Lightnings are in fact a manifestation of plasma. Neon lights, that you have almost everywhere, are basically a plasma. Well, the light that you see from neons is a result of plasma activity, where you make a gas basically enter the state of plasma, thereby being able to conduct electricity and emit light. And I could go on, but essentially, these are a few examples that tell you that there's plasma on Earth, although we may not exactly know it. It's kind of everywhere. And one big topic that you must have heard of at this point is fusion, nuclear fusion, right? We are used to having electric energy produced by nuclear fission, where you take a large atom and you split it in two, and you get energy out of it. What is the holy grail of modern energy research is nuclear fusion, where you take two small atoms and you fuse them into one larger one, and you also get energy out of it. Now, to have fusion, to make fusion possible and profitable, then you need to confine a gas at temperatures which are around 100 million Kelvin or above. And at these temperatures, this gas is going to be a plasma. And the plasma needs to stay inside a reaction chamber, a fusion reactor, what you see here on the right, for example, just a sketch. But there is a little problem, which is that plasmas are gases which tend to behave a little bit strangely. They tend to conduct electricity, which normal gases don't do. And they also are very volatile. So they don't really like to be confined in a region of space, just like gases would do, actually. And especially when they are heated to these extremely high temperatures, it's really quite high to have them, to heat them and to keep them where they are. I will tell something more about this maybe later. Now, my research focuses on plasmas in space, not really on Earth. And when we consider plasmas in space, we have to consider that they exist in many forms. Plasmas in space take many shapes. For example, the sun, that everybody knows, is a giant ball of plasma. Although, yeah, it may not be clear or maybe not so widely known. The sun is made of plasma. It's a giant ball of plasma. And then one of the questions that started popping in people's minds when I say this is how can the sun be a ball of plasma which stays where it is? That's a question that we can discuss later if you want, but I'm just suggesting some food for thought here. What is maybe even less known is that between the sun and the Earth, you're used to thinking that there's some empty space, that between all planets there's just empty space, but this is not true. In fact, between the sun and the Earth, there is plasma. There's the whole of the interplanetary space is filled with plasma. Plasma that comes from the sun, but obviously must be behaving very differently because it's not the sun. So if there is plasma, we can't see it, and it must be behaving very differently. You can go on with this. Each galaxy is made of plasma. Black holes in the universe are surrounded by plasmas. And essentially, plasma is everywhere, really. Between each galaxy, there's plasma. And we can see a little bit about this in this video that I selected for this specific purpose. I hope you can see it. These are videos taken, live observations taken from observatories around the Earth, where you see the surface of the sun liberating plasma in these gigantic explosions that happen periodically. These are different types of observations that show you that these explosions are massive. They liberate a gigantic amount of matter in the interplanetary space. These explosions are many times the size of the sun, actually. And these explosions really are filling the whole of the interplanetary space with material. The interplanetary space is already filled with plasma, but these explosions add to it. Now, what you see here is a little simulation, a little model of how these explosions travel through the heliosphere, what we call the region around the sun. And these explosions can, in fact, reach the Earth. I am pausing here just for a second. These explosions can reach the Earth. And the idea is that, the question is, should we be worried about it? Okay, so essentially, the answer is yes, but luckily we have a shield that protects us. The Earth is a magnet, and as a magnet, it has a magnetic field. This magnetic field of the Earth acts like a shield for the plasma that's coming from the sun. As I was saying earlier, plasmas are gases that conduct electricity and interact with electromagnetic fields, and in particular, they have a hard time crossing magnetic fields. So what you see here in white are magnetic field lines. Plasmas coming from the sun, which will be here on the left, are having a lot of trouble breaking into these lines, thereby effectively reaching the Earth. When you have explosions, this structure that you see here is very heavily modified. It is bent towards the back, it is changing very rapidly. And essentially, during these events, you may have that some plasma particles from the sun can reach the surface of the Earth. That is exactly the moment that on Earth you see auroras. If too many of the plasma particles from the sun could reach the Earth, then it would be a big problem. It would be disruptive because plasma particles being extremely highly accelerated with very high energies can interact with our technology, disrupt electric lines, destroy satellites, and so on and so forth. So these are extremely energetic phenomena that happen regularly, several times a day. You see here one explosion interacting with the Earth. And well, this is a little model that shows you the same thing in sort of 3 dimensions. In essence, what I'm saying is this is an extremely active and dynamic environment which you may not be aware of because you can't really see it, but it is entirely determined by the plasma physics at play. I want to go a little bit beyond the Earth to show you that plasmas are a bit everywhere. As you may have heard, you must have heard at this point in time, in 2019, something grand was achieved by a collaboration of scientists called the Event Horizon Telescope Collaboration. They essentially constructed an array of observatories around the Earth with which they could point the largest telescope ever built to the center of galaxy M87, a galaxy that we know very well in our own sky. The center of the galaxy was visible for the first time, and this was the picture that, that these researchers saw when they could clearly make out the central region of M87. This was called the first picture of a black hole. This is how it was presented to the public in 2019. It reached everybody worldwide. This was a great achievement. But there's a but, which is that one thing that a scientist has the duty to specify is that if you think about it for just a sec, you will realize this cannot be the picture of a black hole. And the reason is that black holes are black by definition, right? They don't emit any light. And therefore, what are we seeing here? This cannot be a black hole. Otherwise, we would just see black. So instead, we're seeing a ring of light. What is this ring of light? Well, this ring of light must be a radiation, light, emitted by matter, which is so hot that is reaching temperatures high enough that quantum mechanical processes are activated. Processes that make individual charged particles, electrons and protons, emit light that then we can see. What could be powering the acceleration of particles to such high energies that they can then emit light? Well, there is gravitational energy to be used from objects that have enough such energies. And these objects can be, well, black holes, for example, right? So what you're seeing in this picture is, in fact, a gigantic mass of gas, of plasma, which is emitting light under the action of a very strong gravitational force, which is making the plasma accelerate to very high energies. What is causing the gravitational force? It's an object we can't really see, but that creates a little depression here in the center, a dark depression here in this ring of light. What can that object be? A black hole. So this picture here is not the picture of a black hole. It is the picture of the light around the black hole. And because it matches our theoretical expectations, it also indirectly proves the existence of an object which behaves like a black hole at the center of galaxy M87. Okay. At this point, I think I convinced you that plasmas are very interesting. They exist in a very wide range of physical conditions, from 100 million kelvins to 100 kelvins even. Number densities that range a span of 30 orders of magnitude. Plasmas have very important practical applications. And yeah, as I showed you, Earth is in fact also at risk due to plasma activity from the sun. But we can also use plasma physics to study space environments which are unreachable in any other way. We don't really have a black hole, next to us that we can go and study. So by using observations of plasma activity around distant objects such as black holes, we can understand black holes themselves, for example. I also want you to appreciate that these plasmas exist on scales which are immensely vast. So what you see here on the left is the jet. It's a jet of plasma. It's in fact a jet of ultra-relativistic plasma traveling near the speed of light. That is in fact coming out from the galaxy I mentioned before, M87. This jet has a size of tens of thousands of light years. But the plasma around the black hole itself may be found in a structure which is maybe something like 40 billion kilometers. That's quite a lot of kilometers, but that's many orders of magnitude smaller than the size of the jet. And if you could go on and zoom into the plasma around in the direct vicinity of the black hole, you would see, a turbulent mess, really, of individual charged particles, electrons and protons, let's say, which tend to have this helicoidal motion, sort of a spiral motion around magnetic field lines. And this motion happens on scales of around 1 kilometer. So you're seeing here a hierarchy of scales that goes many orders of magnitude long. And all over these scales, you're still observing plasma physics. The question is, how can we study then physics that happens on scales which are so incredibly different and vast? You don't have to go as far as studying black holes to appreciate this. I showed you already something like this before. If we look at our own sun, we look at the surface of the sun and we see these explosions that I mentioned earlier, liberating some mass of plasma into the surrounding environment, and also, provoking, causing the emission of some light. In this case, we call this activity flaring activity, which liberate X-rays. So here, you're really seeing at not just a multi-scale problem, but also multi-physics problem, when you have where you have these sort of structures here, which if you could zoom into, you would see as being composed of many substructure, where you would have shock waves, where you would have magnetic traps, trapping particles, where you would have zones that are regions where particles can be accelerated and strong radiation can be emitted. And you would also appreciate that in these regions, you would have particles experiences, for example, turbulent scenarios in which they receive energy from large scales, which is dumped into small scales. You would see combination of waves, heating of the plasma. You would see X-ray emission. You would see the phenomenon we call magnetic reconnection, where magnetic field lines are broken and recombined, liberating energy, etc., etc. It's not just a multi-scale problem; it's also a multi-physics problem with many physical processes involved beyond simple plasma physics, if you want. And so the question remains, how do we study plasmas? Plasma physics is essentially studied in three possible ways, with experiments, theory, and observations. I focus on theory, and theory can be done typically with pen and paper calculations or with numerical simulations. Plasma simulations are a tool that is necessary in modern research, because if we want to solve the equations for plasma dynamics, these equations are very, very difficult. And so if I just give you a set of equations which is extremely hard to solve on a piece of paper, then you will give up and rather maybe think of smarter ways to tackle the problem. For example, by feeding those equations to a computer that can solve the equations for you. And this is a very useful thing to do, because, for example, when you're designing a fusion reactor, such as what you see here, you may not want to build it and do experiments first, because it's extremely expensive and you don't know if it's going to work. But you can do a simulation, or you can do 100 simulations, which will in fact tell you what the best configuration you should use is for building then finally a fusion reactor. You can study systems that are not usually reachable, as I said before. For example, you can appreciate here the structure of the plasma, of how plasma arranges itself in in the surroundings of a black hole with a disk donut structure here and a jet protruding from a black hole, there will be something like maybe here. You can simulate whole regions of the whole universe, actually. What you see here is a simulation of a very large chunk of the whole universe, where each single dot or luminous dot that you see here would be one galaxy. You can simulate the evolution of a large portion of the universe, including each single galaxy, for a very long time, times that we wouldn't be able to observe as humans. You can simulate black holes colliding and the plasma around two black holes colliding, which is very useful for research on gravitational waves, for example. You can simulate all kinds of objects, including neutron stars. What you see here is a neutron star surrounded by plasma, which would then assume this characteristic UFO-shaped structure around it. And, well, I strongly encourage you to interrupt me if I'm going too fast or there's something you want to clarify. But as a physicist, I sort of felt the obligation to show you some equations, which I'm not going to focus on and which I won't force you to understand, I would say. But it's just to make you understand what it means to study, to solve the equations of plasma physics. And here they are. The equations of plasma physics are basically what you see here on this slide. There's the equations for the electromagnetic fields E and B. These equations tell us how the electromagnetic fields evolve over time. There's equations for the plasma itself, which can be seen as a fluid, described by density, velocity, pressure, things that you would use to describe, water, for example, or a gas. Or you can use equations to describe the movement of each single particle, each single charged particle, let's say position x and velocity v, over time. You can solve these two. The idea is that you can couple these set of equations, and if you couple the electromagnetic equations with the fluid equations, then you get a model called magnetohydrodynamics. And if you couple these equations with the particle equations, then you get a model called kinetic physics of plasmas. The two models, the two sets of equations that you get are extremely hard to solve, as I said. So you plug them into a computer and you let it solve them for you. The two models are useful in different scenarios, and I'm not really going to go into detail here, but you're welcome to ask if you want to know more. I just want to mention that one important caveat is that these equations are not always valid, and specifically in the surroundings of black holes and neutron stars. Then you have to take into account relativistic effects. And this changes the picture very much. Your equations change shape, they become very much more difficult. This needs accounting for when you design simulations, essentially. But this is absolutely necessary when you want to study environments where, energies are very high, where, velocities are close to the speed of light, and so on and so forth. The surroundings of a black hole is a good example. I also want to highlight that this is, I hear something.
Just to capture, so you were describing, the trade-off between you do the magnetic portions, but then you treat the kinetics like a fluid versus like a particle. So I guess at what point do the different regimes become important?
Right, very good. Okay, if I can assume that you know a little bit about fluid versus kinetic modeling, what I can say is that essentially what you see here, Maxwell's equations, the magnetic stuff plus particles, would in fact be correct at all possible scales. This is like maybe a bit of a stretch, but let's say that this is more true than not, because essentially that constitutes a first principles description of plasma dynamics. So you should in principle always do the kinetic stuff. But can you? The answer is no. Kinetic simulations, modeling kinetically large systems is impossible. It is impossible due to essentially extreme computational demands. And so if you want to simulate the whole environment around the black hole, it is very, very hard to do it with a kinetic description, but it is very easy to do with a fluid description. Now, what do you lose if you do it with the fluid description? Then you lose information on single particles. So if you want to know, for example, how single particles accelerate to energies close to the speed of light, that's not going to be described by this model. But it's also very important for specific applications, because we do see extremely high energetic particles that come to Earth from astrophysical events, such as supernova explosions or blazars. And this model here, this fluid model, does not describe it for you.
Okay,
So there is a bit of a trade-off, and the answer is not simple, but essentially it's basically on the basis of computational demands and what exactly you're interested in.
so one thing that you're pointing out is in the bottom you have the collisionless model, whereas top is fully collision. And bottom is, I'm thinking like nuclear reactor, particles flying around just side by side. But when you have more like a molecular dynamics, where collisions or particle-particle interactions are important, is there a major regime like that, or is collisionless the more common one?
So I can say two things. First of all, that in astrophysical plasmas, collisions between plasma particles tend to be very rare in general, and the reason is because these particles are charged. They tend to just not interact with each other. The electric forces between them tend to prevail and essentially prevent them from touching each other, physically touching each other. Now, this is not true in all possible scenarios, but it is true in very much many scenarios. And therefore, the collision-less model is most often than not correct. Now, if you want to add collisions, you can. There are algorithms for that, which I'm not highlighting here, but they can be incorporated in the kinetic description.
And just the mental model, I mean, you're describing a plasma as a bunch of roughly speaking, a bunch of protons and a bunch of electrons. Electrons, fly away, protons fly away, but those two attract each other. So to what extent is that the collision between oppositely charged particles a big deal, or do they just
right? But so they attract each other, yes, but just like they don't touch each other in an atom, they wouldn't touch each other if you make them go against each other. Electrons will be attracted to ions, but they would also not physically touch them. They'd rather skim them. They'd rather graze them and go around, right? And this is ensured by the fact that we're talking about quite energetic particles. So there is no danger that, for example, well, at least in the applications I'm going to highlight, there is no danger that there is a sort of recombination in which electrons and ions, electrons and protons are going to stick together again. Again, this is not true in all scenarios. In fact, on the surface of the sun, there are also a lot of recombinations in which protons capture electrons and also release them all the time, which is something you have to take into account in some models of the solar surface. So, yeah.
Cool. Thank you very much.
Yeah. Happy to be interrupted again if you guys have more questions. I'm happy I could go more technical, but I'm also trying to stay not too technical. So please interrupt me if you have more clarifications needed. Right. So I was about to say that these simulations are extremely intensive. Whether you use the fluid model or the kinetic model, these simulations are always extremely intensive. They require supercomputing facility. They require high performance computing. And typical simulations use, hundreds, thousands, tens of thousands, hundreds of thousands of CPUs to essentially conclude calculations within a human lifetime. This is very routine. Using hundreds of thousands of CPUs is quite routine at this point in time. And recently, the trend is to actually start using GPUs, which is something that we as scientists are a bit late on. If I can give my own opinion, GPUs have been used for stuff for a long time. In science, using GPUs is a matter of the last maybe 5 years, which is becoming like predominant, I would say. So everybody's moving to GPU calculations now. But of course, finding resources for these calculations is kind of hard, and you also have to consider what the environmental impact for these sort of simulations is. I mean, supercomputing centers can absorb a lot of power, can produce a lot of heat, which needs to be handled. Not an easy problem. Now, provided that these resources exist, and I was highlighting here a couple of superclusters I used recently in my research, then we can maybe I can try to exemplify a bit what kind of applications we at KU Leuven have been working on in recent years. I already said sort of everything that's on this slide. What I'm going to try to also keep in mind in the rest of these slides is that the scales, the length scales, if you want, length and time scales, that you can take into account go from microscopic to macroscopic. The regimes that are applicable for various applications can go from, well, the fluid to the kinetic regime, exactly what we discussed before. And that the energies that you can span are from non-relativistic or Newtonian to relativistic regimes. The approaches that we use vary significantly depending on where we are and on these arrows. And that if extra physics is needed, then you can always add it. As I was mentioning before, you can add collisional effects. You can have multiple particle species, radiation, QED, these quantum electrodynamic effects, forcing of the plasma in the case of expansion, for example, and so on. So with that being said, let's start from sort of quote-unquote low energy applications, the heliosphere, you know, the region of space surrounding the Earth. The heliosphere has, well, we think it has a structure more or less what you see here on the slide, where the sun is in the middle and it's surrounded by several cocoons of plasma with different properties. What are the main plasma structures in the heliosphere? Well, on the sun, we have the sun itself, effectively, the solar corona, which is the outermost layer of the sun, with structures such as coronal loops, which are essentially arcades of magnetic field that traps plasma. We have the solar wind, which is a continuous stream of particles that escape from the solar surface and fill the interplanetary space. We have the planetary magnetospheres, the region filled by the magnetic field of the Earth, for example, that prevents plasma from the sun to come to the Earth. And we have a bunch of phenomena which I already highlighted. We have explosions, which we call coronal mass ejection. We have the expansion of the solar wind. We have turbulence in the solar wind. And I could go on. You get the picture. We study each of these structures and phenomena with different approaches. For example, here you see a simulation done by my colleagues, where we can simulate the whole environment around the sun. And here each single dot is a different planet. And we can study how explosions from the solar surface happen and how the magnetic structure of such explosions look like here, for example. We can study individual structures on the surface of the sun, such as coronal loops. We make simple, typically actually quite simple models of them. For example, here you see a representation of a coronal loop in a simulation. And inside such a coronal loop, we can appreciate turbulent plasma, dissipating energy, accelerating particles, and producing X-rays, for example. We can study explosions from the sun, again, with simplified models. We can study how, for example, such explosion would propagate in a piece of, well, in a region of the heliosphere. And we also know that at the front of such explosions, we can have very efficient particle acceleration. Now, I'm going to mention particle acceleration a few more times because effectively what is dangerous for us as humans or in our applications are very strongly energetic particles. These particles tend to really interact very strongly with everything, including humans and spacecraft and materials that we have. So a big question is how they are accelerated to high energies, how to detect them, how to predict phenomena that may accelerate particles very strongly. So at the front of these explosions, of solar explosions, we have what we call shock waves, and these shock waves are where particles may be accelerated very efficiently. So we sort of need to study them. in the solar wind, in this continuous stream of particles from the surface of the sun, there's a wide variety of phenomena that happen, which include turbulence, and turbulence can dissipate energy from large to small scales, thereby, again, accelerating individual particles. And so we need to study the solar wind, and we can study the solar wind emitted by the sun. We can study how it develops turbulence, and how it determines particles accelerating, okay? Oh yeah, this is my student Sylvia, who's studying here at KU Leuven. She is studying the interface of the Earth and the solar wind. So you see here a representation of of the plasma structure that would be surrounding the Earth when the Earth interacts with the solar wind. We would create such a cocoon structure. And at the interface of this structure with the solar wind, you have interesting plasma phenomena where plasma from the two regions tries to mix. You can simulate this, and this is what you would see. You would see a sort of instability developing. You would see plasmas once again developing turbulent structures, which once again can result into mixing and particle acceleration. We can go to a bit high energies, the surroundings of black holes that I mentioned before. You can, well, I want to highlight that maybe something that you should appreciate here is that there is a difference between what you see if you could observe, well, what you would see if you could observe a plasma around a black hole, which would be the video here on the right, and what actually that plasma is, how the structure of the plasma is, which is what you would see here on the left. There is a difference between these two pictures. Here you see a jet region, here you see, a jet region, here you see a disk region, black hole here is here in the center. And here on the right, you see, well, you see more of a distorted picture. You see some turbulent mess, which, yeah, resembles what I just mentioned, but also shows some quite significant differences. Why is that? The reason is that when I consider what we call compact objects, when I consider black holes, then I have to consider that what I see, what the light that reaches me, does not describe accurately the structure of, in this case, the plasma, of the emitter of the light. And why so? The reason is that a strong gravity, such as that exerted by black holes, is bending light. You may have heard about light bending before. It's a bit of a difficult concept because light doesn't have mass, right? Light is photons. Photons are massless particles. They don't have mass, so how do they respond to gravity? Well, special relativity theory by Einstein from 100 years ago tells us that, well, light is made, in fact, of particles with zero mass, that mass is equal to energy, the time is equal to space. And then general relativity tells us that mass, which is energy, creates what we call space-time curvature. It essentially modifies the space-time around it such that particles, either massless or with mass, have to follow trajectories which are not straight lines anymore. And so light rays emitted by some plasma, they try to go on a straight line and reach my eye, but around the black hole, they won't. They will, in fact, move according to some very complicated trajectories, which will then bring them to some other places. And therefore, the picture that I will see does not represent one-to-one the structure of, let's say, plasma flows, for example. This needs to be taken into account because, as you see in this figure, you can have very, very severe distortions. What you see here are simulations of light rays emitted, let's say, by, I don't know, a flashlight here, this red dot that you see here, which would try to shoot light rays in a straight line, these blue lines here. But instead, around the black hole, these light rays will be heavily bent and reach other places. And what you see here on the right is that this phenomenon can go as extreme as determining trajectories of photons, which are, well, closed. they are bound trajectories. They are trajectories where photons will never get out, which means that these photons are effectively trapped. They will never get out of here. They will never reach your eye. You can see them if we simulate them, but if we were to look at a black hole, these photons would never reach our eye, and therefore we wouldn't have a picture. Yeah, let me skip this, but the overall result of this is that light bending creates stunning pictures that you might have seen before, for example, in the movie Interstellar, which looks something like this typically. And these calculations of how light bends need to be taken into account when we compare simulations and observations. Okay, if
So
that is
about
yes?
the basic dynamics here. First of all, what we just saw was a disk, like a warped disk around the black hole, right?
So the figure you see here could be a number of things. One of the things that could be is that you would be seeing light that comes from the back of from some distant object in the back of a black hole. It could also be indeed a disk, a very thin disk of material that's emitting light that is in orbit around the black hole. In all cases, the idea is that you are seeing a very different picture from what you would be expecting. You are seeing not a disk or not a light source from behind the black hole. You're seeing some distorted image in which you see, well, in this case, if it's a disk, you would see actually all parts of the disk, not just the front. You will be able to see also the back of the disk because of how light is bent.
And then because this is I'm getting the impression this is a plasma charged disk, then the planetary system, it's gravity that's pulling everything together. But here, there's a bunch of plasma that's pushing everything in crazy ways. Why would it stay a disk?
Okay, so you don't need to make any assumption about what exactly this disk is. Let's assume, which is actually, I think, how these calculations run. Let's assume that this is just a disk of material. It could be plasma, could be anything that's emitting light, and the only purpose here is to see where this light is going. Now, your question is legit. Why would that disk stay there? Well, a black hole is not, as an entity, as a structure that we see from the outside, is not different from a star, right? We orbit around the star on the Earth. We orbit around the sun, and we don't fall onto the sun, right?
Right.
Why so? Because yeah, the sun is pulling backward, but at the same time we are moving forward, and the resulting motion between these two is a curved path, right, which closes onto itself, and so the Earth will never fall into the sun. Now, a black hole does the same thing to matter and also light. So if I am, just a blob of matter around the black hole, I don't have to fall in if I have enough angular momentum that keeps me on an orbit. Light is the same, although it's a bit difficult. It's a bit weird to talk about angular momentum or momentum for a ray of light. Light is sort of the same, right? Now, of course, this is a bit misleading because I'm describing gravity as a force, whereas what I said before is that in fact, gravity is bending of space-time. So in fact, the truth is, or how we understand it is, in the surroundings of a black hole, a straight line is not a straight line, it's a curve, and stuff is bound to move along this curve. How you see this disk staying there is because there are curves where matter and light have to travel, and these curves are closed onto themselves, so stuff will never fall into a black hole. Now, not all curves are closed onto themselves, and not all matter can stay in orbit, but if some matter can stay in orbit, this is how it would look like.
Okay, so now, normally when you see, like, I think what I'm wondering about is why is it a disk specifically? And maybe that's not the case, because I would have expected, like, galaxies, a disk, it's mostly neutral. Planetary disks are just, they're almost neutral, they staple down. But I was expecting something like a black hole to look like the video before, where they just all go in crazy directions from up, down, and left, right, because of all the much more complicated interactions, because it's a much denser kind of environment that's also charged.
That's right.
Yes or not?
Right. That's right. But what you see, so that's exactly the point. What you see here as an observer are only the light rays that are reaching you.
Right.
Right. So this is really your eye reaching, receiving some light rays. So basically, what I'm saying is that, you know, if there are some rays of light that travel around the black hole, an observer will only see the ones that reach it. If you can think of it in this way: take the end point of these rays of light, go around the black hole, and then reach your eye. You will see whatever these light rays are bringing you, but you won't see anything else. Okay. In this case, what you see here are basically the light rays that are reaching your eye, and wherever they originate, you don't know. And all the other light rays that are not reaching your eye, you're not seeing. You know, yes, there may be crazy trajectories, there may be crazy stuff going on, but you're only seeing whatever light rays are reaching your eye as a point observer.
So we only see stable orbits that ultimately,
yeah, exactly.
And that's exactly right. Fall in, for example.
That's exactly right. So, for example, you see here that these orbits here are light rays that are stably bound to be around the black hole. Now, these we can simulate, we can observe as in a simulation, right? But if I were to be an observer around the black hole, I would not see this light because it wouldn't reach me, right?
Interesting.
Like,
okay.
these would be light rays that are trapped on bound orbits that I can simulate them on a computer. I can appreciate them. But if I were to be an observer, I wouldn't be able to see them because this light doesn't reach my eye, and therefore I don't see it. You see?
Got it. So, and even if I was inside a black hole, I wouldn't see them either because they are just stable, weird orbits.
Yeah, that's right. That's right. In the same spirit, why is this all black? Well, this is all black because no light rays are coming from, well, the region that is here to my eye.
Right.
Right. That doesn't mean that there isn't light here as a physical space. It means that I don't see it.
Right. That makes sense. Thank you.
It's really quite difficult. This is a good question that you asked me, but it's really quite difficult to accept that you don't see a one-to-one representation of reality, right? Yeah. In everyday light, like I look straight in front of my face and I see the object that is in front of me. Why? Because there's a ray of light that goes on a straight line from me to it. Here, you have to give up this concept. All right. So if you're convinced about that, which is already quite mind-bending to stay on topic, then yeah, if we take into account all these phenomena, then we can actually try to match observations and simulations. Typical observations are what I showed you before. Typical simulations tell us that the structure around the black hole looks something like this. I also sort of showed you this before. This is a cut of a simulation, much bigger simulation, where you would see an accretion disk, you would see a jet, and you would see a region in between, which we may be tempted to call something like a corona, which because it very much looks like the solar corona, the outermost layers of the sun. What you see here on the right is that the simulations of black hole environments are well, have reached a very late maturity, I would say. Here you see a gigantic simulation done by my friend Matthew Diska, who actually used GPUs to simulate the whole environment around the black hole. And in this case, he could make simulations which are so big and so long that show you that a disk around the black hole, or the disk of plasma, when it's tilted, it can even break up and be disrupted and create substructures, sub-disks within it. So this was a really a heroic simulation, a pioneering simulation of plasma dynamics around the black hole. Okay, going a bit smaller than that, when we simulate black hole magnetospheres, we simulate, well, a typical simulation looks like this. It is the environment around the black hole with the plasma reservoir around it. And you can appreciate here that we're seeing it from the side, that you can appreciate that this plasma assumes very turbulent properties. Turbulent properties that result in structures such as what you see here on the right, and potentially result in phenomena such as flaring activities, the same flaring activities that I highlighted before around the sun, essentially. And sorry about that. I'm being called on the phone. Okay, so I was mentioning that the sun has these flaring activities where light is liberated, where magnetic energy is liberated, where explosions are essentially liberated in its surroundings. The same happens for black holes, and we can see this through these simulations. Now, these simulations are, well, 2D cartoons of full 3D simulations, I would say. But the interesting bit is that this flaring activity, these explosions, these bursts of light, is something that we do observe from centers of galaxies, such as even our own galaxy. So this is very nice because we have an explanation for something that we see in the sky, but we can't really measure. We can't send spacecraft to the center of the galaxy. We can go a bit more in detail when we study black holes and their surroundings. Here you see the disk around the black hole. And one possible approach to understand the turbulence inside the disk a bit better is to extract a little piece of the accretion disk, and run what we call a localized simulation. You extract a little piece of it, and then you can study it in very much more details. This is what my postdoc, Gene Gorbunov, has been doing already for some time, as well as my collaborator, Astro Sandoval. What you see here is essentially that these simulations give you a very detailed view on the plasma turbulence in the black hole disk, which can be studied because, once again, it implies that energy is being transferred across scales. And when energy is transferred across scales, specifically from large to small, then you can expect particle acceleration. Now, in these environments, particle acceleration brings particles to very high energies, ultra-relativistic energies, at which they can potentially emit light. So once again, we may try to understand the light that we see by understanding the plasma dynamics. In the regions around the disk, I already sort of mentioned that there is a region which we may call the corona. The region that we call the corona is something like a very strongly magnetized environment, very underdense, very strongly magnetized, where you have a lot of free magnetic energy. Magnetic energy which is stored in magnetic fields. If you can liberate this magnetic energy, then once again, you may think that particles could be accelerated by absorbing this energy from large scales. My collaborator, Daniel Grosjean, has been studying this for a while, and we have seen that indeed in these environments, very strongly magnetized plasma turbulence can accelerate particles to extremely large energies, extremely high energy, so high that you can produce X and gamma rays. Another phenomenon is what I mentioned before, magnetic reconnection, where you see magnetic field lines coming into contact and breaking up, thereby liberating energy. This is once again a phenomenon that could be accelerating particles very strongly up to extremely large energies. Yes, I want to highlight that the simulations I showed so far typically focus on one of the two regimes I mentioned earlier, either the fluid or the particle kinetic approaches. But there's more to it. In fact, you can try to merge the two approaches. You can try to use them both at the same time. For example, by using large-scale fluid simulations, to which on top you add individual particles to study their own individual motion. So here what you see on the left is exactly this. It is an underlying fluid simulation where on top you can place particles and then you can trace them through the flow. Now this means, however, that you have to take into account general relativity in the particle motion, that you have to take into account small-scale kinetic effects on large scales. And this changes the interpretation of these results very much. You can do this for black holes, you can do this for neutron stars. What you're seeing here on the right is in fact a global simulation done with kinetic physics. So the whole environment around the black hole, but with individual particles. This was a very, well, it was a bit of a breakthrough results that we got a couple of years ago when the methods that we use for these simulations became mature enough that we now can actually do this.
So question,
and yes,
how do you validate any of this? So I mean, you have some light coming out of the black holes and some, collisions you can capture, but for the most part, a lot of these dynamics are invisible to us.
That's right. That's a very good question. Oh, That's the worst question you can possibly ask a theoretical astrophysicist, because the answer is you can't really, right? This is a big open question. How do we validate these results? And there, at this point in time, the community has developed a few common strategies. First of all, one of them is to check if, for example, in such a simulation, in the simulation of our neutron star here, the energies that are reached by my particles are high enough to be compatible with light emission mechanisms that give me, let's say, an X-ray spectrum, which is the one that I actually observe in the sky, right? So if I can show that in this simulation, my particles reach an energy which is high enough to that they actually emit light, then I can effectively construct a fake observation, a synthetic observation of, let's say, X-ray emission that I can then compare to real observation. And I'm a bit sad that I didn't put it here, because my collaborators have been doing this for quite some time, and we had recently very good results in matching simulation results with the energy spectra retrieved from X-ray binary systems, for example. So this is possible, and it is routinely done. But of course, what I just talked about is an approach in which you take all this dynamics here, you collapse it into one line, one synthetic emission spectrum, and you compare it with one other line. Of course, this can't be the full picture, right? Because you're effectively reducing yourself very much with respect to the data you have. And so you can go further. You can try to compare the timescales of the flaring emission, for example, with the timescales of the variability we see from the center of the galaxy, let's say. You can compare the expected neutrino emission from these simulations to the actual neutrino emission that is observed. You can compare different models with each other and see if they give you sort of compatible results. Because if they do, then it's a bit of a reinforcement that what you're doing is kind of right, etc., etc. This, in general, is an extremely difficult task.
It makes sense.
Yeah. That's kind of all I had to say, really. I hope I convinced you that plasmas are cool, that the studying them is worth it from a fundamental standpoint, but also for practical application. We have models for that. We have fluid and kinetic models. We apply these models over very, very large ranges of scales, essentially. Some basic plasma processes that I went to time and again are ubiquitous in the universe. Turbulence, reconnection, particle acceleration. This is good. It means that the more we understand them, the more we can interpret observations from very diverse environments. And ultimately, yeah, we would like to uncover, unknown processes that we observe in the universe that give rise to the radiation we see. We would like to explore environments such as black holes which can't really be reached, and potentially even probe the validity of general relativity. We can, in fact, apply all this knowledge to protect ourselves from dangerous solar activity. And as scientists, of course, we can have fun with it. So I'll close with that, and I'm happy to take more questions if you have them.
Cool. Well, thank you very much. One thing that I'd like to know is, you've been focusing on stellar and black hole regime plasmas. What are the nearest, I guess, terrestrial or engineering use cases that are more
That's right. So I focused on my own research, obviously, but so the interesting bit about all of this is that our methods, the methods we use in the community, are very general. So people who study nuclear fusion, they in fact run simulations of tokamaks, of fusion reactors, with basically exactly the same methods.
Right.
Like the methods only solve a set of equations. They don't really care about the physics you do. The physics is determined by, the geometry of your system, the initial conditions, the boundary conditions, but the methods themselves can be applied to basically anything you want, right? And the interesting thing is that, it's not in this presentation, unfortunately. Yeah, the interesting thing is that these methods are not even just methods for plasma. You can do simulations of many more things based on exactly the same principles. You can simulate just gases. You can simulate, if you go to kinetic modeling, you can simulate a lot of stuff like molecules and the things you actually mentioned before, right? You can simulate all sorts of kinetic processes, and you can even use the same models to simulate something like structural mechanics. So in the movie Frozen, that you must have seen if you have children, they used basically exactly the same methods that I have used to simulate some of my plasma stuff, but to simulate snow dynamics. So it's literally exactly the same numerical approach, but for something that's completely different, right? So there's a lot more to be learned from all this process than just plasmas around black holes. It's wider than that.
Cool. And then so you give a bunch of examples of stars, but if I wanted to do a full star, then I have to worry about, I mean, you're focusing on coronal kind of stuff. But if I go into the body, there's definitely a bunch of plasma stuff, as well as high temperature transport and some fusion processes, which are presumably nuclear force something. And if you go a dying star, you have like real chunky elements going on here. So how do you couple these dynamics with all these other internal dynamics?
Yeah, that's you're absolutely right. So in this sense, black holes are easy because you don't have to care about their interiors. Whatever falls into the black hole is lost forever, so you can just forget about it. If you want to simulate stars, I strongly encourage you to look it up. There's groups who simulate the whole layers, the entirety of the layers of a star from its core to its surface. And that requires plasma dynamics, it requires gravity, it requires radiation physics, it requires thermal stuff, it requires a lot more stuff than just what I showed you, right? But it is possible. You just combine a bunch of different physical ingredients, you make a gigantic simulation, and you have it. Of course, in that case, because you have so many ingredients, it's very hard to tune all of them. And that's essentially the complication of these extreme multi-physics simulations. But they do exist. And I have a good colleague in Amsterdam, Philip Mustam, who recently produced one of the biggest ever simulations of supernova explosion, from the star to the explosion to the final compact object that remains behind. You just have to take into account a crazy bunch of different physical things, but once you do, in principle, you're done, right?
Got it. Well, yeah, then that's really clear. Thank you very much.
Yeah. Thanks for this opportunity. Yeah, again, I can be reached by email. If anybody has more questions, you want to connect, please hit me up. Yeah, and thanks once again for having me.
Thank you. Have a great night.